This script imports essential libraries such as NumPy, SCIP, Matplotlib, Pandas, Pandas DataReader, TensorFlow, Keras, Scikit-learn, Sklearn, StatsModels, and more in Python. NumPy and Pandas facilitate data manipulation and analysis. Matplotlib is used for plotting graphs and data visualization. TensorFlow and Keras are utilized for constructing and training neural networks. Scikit-learn Sklearn is a machine learning library for tasks like preprocessing, model selection, and evaluation. StatsModels offers classes and functions for estimating various statistical models. Pandas DataReader provides a method for retrieving financial data from online sources. By leveraging these libraries, one can engage in diverse activities like data analysis, machine learning, deep learning, statistical analysis, time series analysis, and more within Python. These libraries offer robust tools and functions to simplify the development of machine learning models, statistical analysis, and data visualization. Importing these libraries is crucial for accessing their functionalities in your Python projects. The following code utilizes the pip package manager to install the Python library named pmdarima, which provides a user-friendly interface to ARIMA models in Python. ARIMA models are commonly employed in time series analysis for predictive modeling. By executing this code, one can efficiently install pmdarima in their Python environment, eliminating the need for manual downloading and installation of the library. This code provides a standard setup for conducting time series analysis and forecasting tasks efficiently. It begins by importing essential libraries for data handling, visualization, statistical analysis, and machine learning. Warnings are suppressed to ensure a clear and concise output. The libraries employed include NumPy and Pandas for data manipulation, Matplotlib for graphical representation, StatsModels for time series analysis, ARIMA for forecasting, and pmdarima for automatic parameter selection in ARIMA modeling. Moreover, functions for computing metrics like mean squared error and mean absolute error are imported. By utilizing this code template, all the necessary tools and libraries are readily available for conducting time series analysis and forecasting, streamlining the process and eliminating the need to repetitively import the same libraries. The following Python script uses the finance library to fetch historical stock price data for the stock symbol Lieutenant. It's from Yahoo Finance API. The explanation of the code is as follows. 1. The line imports iffinance as if imports the iffinance library and provides the alias if for referencing its functions and classes. 2. The line import datatime imports the datatime module for handling dates and times in Python. 3. The line ticker Lieutenant needs defines the variable ticker with the stock symbol Lieutenant. 4. The line start date datatime at 2022 3 creates a datatime object representing the start date January 3, 2022. 5. The line end date datatime at 2024 1 creates a datatime object representing the end date February 1, 2024. 6. The line diff download ticker start date and end date uses the download function from the finance library to retrieve historical stock price data for the specified ticker between the start date and end date. The data is stored in a Pandas DataFrame key for further analysis, visualization, or processing. In brief, this script fetches historical stock price data for the Lieutenant and stock from Yahoo Finance API within the specified date range, facilitating financial analysis, research, and the development of trading strategies based on historical stock prices. The diff command, short for disk-free, is a Unix and Unix-like operating system tool utilized to display information regarding the available disk space on a file system. Running the diff command in a terminal provides a list of mounted file systems, detailing data such as total size, used space, available space, and file system type. This command is valuable for managing disk usage and ensuring sufficient available space for data storage and program installation. It aids in detecting potential issues like a full disk that could impact system performance, prompting necessary action to prevent problems. In essence, utilizing the diff command offers a convenient way to monitor disk space usage on a system, making it a beneficial tool for system administrators and users wishing to track their disk utilization. In Python, using the Pandas library, the diff shape code snippet is utilized to obtain the dimensions of a data frame. It provides a tuple with the count of rows and columns within the data frame. The initial item in the tuple signifies the row count, while the second item denotes the column count. This piece of code is beneficial for promptly assessing the dataset size or confirming the row and column quantities before conducting additional data operations or analysis. A thorough comprehension of a dataset's dimensions is crucial for a variety of data manipulation and analysis activities. This code snippet uses matplotlib to create a plot figure with dimensions of 12 x 6 inches. The plot displays the opening prices from a pandas data frame likely named diff on the x-axis against the date on the y-axis. It specifies the plot's title as opening price and labels the y-axis as date and the y-axis as open price. Employing this code is crucial for visually representing data to extract insights. In this scenario, the code visualizes the historical opening prices of a financial asset, aiding in the identification of trends, patterns, or irregularities in the dataset. Plotting data facilitates the interpretation and analysis of the information, enabling us to derive meaningful conclusions from the dataset. The script instantiates a new figure object with dimensions of 12 x 6 inches for plotting a graph. It proceeds to plot the closing price data from a pandas data frame, where the x-axis denotes dates and the y-axis denotes closing prices. The graph is then displayed with a designated title, date as the x-axis label, and closing price as the y-axis label. Utilizing this code allows us to visually represent the closing price data across time, enabling the observation of trends, patterns, and fluctuations within the dataset. Such visualizations can aid in decision-making based on the data insights and effectively communicate information to others. The code snippet below performs the following tasks. 1. Split the data frame diff into training and testing data sets with an 80-20 ratio. 2. Plot a graph using matplotlib pplot to display the closed prices of the dataset. The graph shows closed prices of the training and testing data in different colors, training data in blue and testing data in green. 3. The graph is titled and includes x and y-axis labels, as well as a legend for distinguishing between training and testing data. This code is crucial for evaluating predictive models as it allows the visualization of model performance on both training and testing datasets. The graph aids in analyzing the model's generalization capabilities, identifying potential issues such as coverfitting or underfitting, and assessing the accuracy of the model's predictions. The following code snippet demonstrates time series forecasting using the ARIMA model. Here is a breakdown of its functionality. 1. It imports necessary libraries including NumPy for numerical operations, the ARIMA model from StatsModels for time series analysis, and mean-squared-error from Sklearn for calculating mean-squared error. 2. It defines the SMAPE function to compute the symmetric mean absolute percentage error SMAPE to assess model performance. 3. Two arrays trained R and test R are created to hold historical and test data values. 4. The history list is initialized with values from the training data. 5. The code then iterates through each data point in the test set. 6. In each iteration, an ARIMA model is fitted to the historical data using an order parameter 5, 1, 2, which represents the autoregressive, differencing, and moving average components. 7. The next data point is forecasted using the fitted ARIMA model and added to the predictions list. 8. The actual observed value is included in the historical data for the subsequent iteration. This code can be utilized to train an ARIMA model on a given time series dataset, e.g., stock prices, to predict future time points. ARIMA models are commonly employed in time series analysis for forecasting as they can capture autocorrelation and seasonality patterns in the data. By fitting an ARIMA model and conducting predictions, we can analyze and anticipate future trends in the time series data. This code assesses the performance of a predictive model by calculating various error metrics between the actual values testor and the predicted values predictions. The metrics evaluated are 1. Mean squared error MACE. This metric represents the average of the squared errors, indicating the average squared difference between the predicted and actual values. Lower MACE values signal a more accurate model fit. 2. Symmetric mean absolute percentage error SMAPE. SMAPE determines the average percentage error between the actual and predicted values. A lower SMAPE value signifies improved model performance. 3. Root mean squared error. RMS is the square root of the mean of the squared errors, providing the average of the square root of the sum of squared differences between predicted and actual values. RUMS is particularly useful when significant penalties for large errors are required. 4. Mean absolute error may calculates the average of the absolute errors between predicted and actual values. May is less influenced by outliers compared to MES and RUMS. Utilizing these error metrics assists in evaluating the model's performance, offering insights into prediction accuracy and reliability. They support the comparison of models or parameter tuning to enhance overall model performance. This code creates a plot to compare predicted stock prices with actual stock prices. It utilizes a visualization library like Matplotlib to generate a figure of specified size, showing historical close prices as training data, predicted prices on test data with markers and dashed lines, and actual prices on test data for comparison. The plot is titled like Prices Prediction, with the x-axis labeled as dates, the y-axis labeled as prices, and a legend added to differentiate between training data, predicted prices, and actual prices. This code is essential for evaluating the performance of a machine learning model in predicting stock prices. It enables analysts and stakeholders to visually compare the model's predictions with the actual stock prices to gauge its accuracy. This snippet of code is commonly utilized in Python with libraries like Matplotlib to produce a line graph visualizing the predicted and actual prices of the Larsen-Toubro stocks. The code creates a figure with a specific size, where the predicted prices are represented by green markers connected by dashed lines, while the actual prices are shown as a solid red line. The graph's title is set as Prices Prediction, with the x-axis labeled as dates and the y-axis as prices. Additionally, the code includes a legend to distinguish between predicted and actual prices in the graph. This code is crucial for assessing the performance of a predictive model that aims to forecast stock prices based on historical data. By displaying both predicted and actual prices on the same graph, it enables a quick and intuitive comparison to evaluate the accuracy of the prediction model. The graphical representation simplifies the identification of any discrepancies or trends between the predicted and actual prices across the chosen time frame. This snippet of code is integral to a machine learning process where actual values from a dataset test are compared with predicted values. Here's an overview of how it functions. 1. First, it creates two pandas data frames, one for storing the actual values in a column named actual and another for storing the predicted values from a list called predictions in a column named predicted. 2. The code then resets the index of both data frames to ensure proper alignment and that they start from 0. 3. Subsequently, it combines the actual and predicted data frames into a new data frame named output along the column axis tones. 4. Lastly, the code displays the last 10 rows of the output data frame, showcasing the comparison between actual and predicted values. This code is crucial for evaluating a predictive model's performance by visually comparing its predictions with the actual values. Such comparisons aid in gauging the model's accuracy, identifying discrepancies for further investigation, and are commonly utilized in machine learning for presenting results in a tabular format to facilitate analysis and decision-making. The following code computes the symmetric mean absolute percentage error SMAPE accuracy for a given set of predicted and actual values. Here's a summary of its functionality. It defines a function named SMAPE that accepts two parameters, eTrue for actual values and ePred for predicted values. The function calculates SMAPE using a formula that involves computing absolute differences, dividing by the sum of absolute values, averaging the result, multiplying by 200, and returning the value. This function enables the calculation of SMAPE for the provided values. The code then determines the SMAPE accuracy by subtracting the SMAPE value from 100. SMAPE is typically represented as a percentage error. This step involves utilizing the actual and predicted values from the dataset. Lastly, the code displays the computed SMAPE accuracy value. SMAPE is a widely used metric in forecasting and predictive modeling for assessing the precision of model predictions relative to the actual data. It is favored over other percentage-based error metrics like MAPE due to its handling of zero values and symmetric error representation. By evaluating the error between predicted and actual values, this code offers insights into the forecasting model's accuracy